Okay, perfect. So thank you for this invitation and for this opportunity to present you the work of Solnil. So I will go through the inorganic material we developed for fabrication of optical metasurfaces. So first, a few words about Solnil. So we're a startup. We started in 2020. 12 today, and our main focus is really to develop material and processes for micro fabrication, mainly for optical applications such as augmented reality, laser optics, and optical metasurfaces. So I've been fortunate to have the support of various French agencies like BPI, DGA, and more recently we got a grant from the EU, the EIC transition, that allow us to upscale our pilot line from 2-inch 50mm to 8-inch as ongoing. So what are the materials that we are developing at Solnil? So what we developed is a soil gel chemistry that allow us to deposit a wide range of metal oxides, silica, titanium mainly, using simple liquid deposition processes, such as spin coating, deep coating, and spray coating. And using these simple processes, we can deposit high quality optical coatings, which have also the benefits of being compatible with nano-imprint lithography. So it could be both used to make optical coatings or nanostructured surfaces. Since our materials are purely inorganic, they have the advantage of being highly stable with temperature, UV, or mechanical stress. They can also withstand high humidity. And one of the distinctive features of what we do is the control of refractive index. So we can go to very low refractive index from 1.11 up to 2.6 for visible light, which is quite unique. Regarding the process options, so our main focus today is nano-imprint lithography, which is what we developed for augmented reality applications, where you need to make these slanted gratings or binary gratings, like your shoulder layer. And it's suitable, direct nano-imprint is suitable for aspect ratio up to 4:1. When you go to more challenging aspect ratio, although you see some publications about direct nano-imprint of high aspect ratio, I think the easiest way and what most of the industry is doing today is to use traditional top-down etching approaches, which are used today in the semicon industry or with microelectronics. And what we propose there is just to replace atomic layer deposition or PCVD by a coating made by spin coating to reduce the cycle time. And then you can use your standard process based on nano-imprint lithography or deep UV to etch this layer. So now if we come back to the refractive index range that we can cover, why is it important to have such a refractive index contrast? Usually when you work on a metasurface, the base building component is what we call a meta-atom. So you have these pillars usually of high refractive index materials, and you play on the dimension to have a full coverage of the phase, develop your metasurface. And usually for integration into a product, you need some kind of encapsulation layer to protect this metasurface from mechanical damages and to have better integration into your product. And what is important there is the refractive index contrast of this encapsulation layer with the metasurface. So if we take an example, and it was done with the help of PlanOpSim for the simulation. If you want to make let's say a design for visible light at 520 nanometer, if you use a material with a refractive index of 2.3 and encapsulation layer of 1.5, you end up with having to etch pillars with a height of 1.2 micron. On the other hand, if you can increase the refractive index contrast, so if you can go to a refractive index of 2.5 for the metasurface, and to reduce the refractive index of the encapsulation to 1.12, now you need only 600 nanometer pillars height. So it has a kind of huge impact on the processing. So using this wide range of refractive index allows you to simplify your process. So now, how did we achieve such high and low refractive index? So the high refractive index, we obtain it using kind of specific TiO2 formulation. So we start not with nanoparticles, it's something smaller. We start with molecular precursors, and we have building blocks, which are quite specific. They have a kind of hard core and kind of soft shell. So when you deposit this material by spin coating on a layer, and when you have this drying, the soft shell tend to merge, and basically what you end up, you end up with a very compact and dense layer, which allow us to get this very high refractive index. And as you can see, we managed to have very small crystal grains, which is why we managed to obtain, even for very high refractive index, this very low scattering or absorption. So here's some kind of SEM pictures of gratings we obtained with our process. On the left is kind of standard salt gel, which is not controlled. If you don't control the crystallization, you end up with very big crystals, like you see on the left, which will cause a lot of scattering and loss. What we achieve at Solnil is that we managed to keep and to control this crystal growth to have kind of very dense layer with no scattering by keeping the crystals below 6 nanometers. This is the key to achieve a refractive index and optical quality. For the low refractive index, the approach is quite different. So what we start with a silica formulation. So we have a formulation that can, after curing, become pure glass. And what we did is that we managed to control the porosity of this layer. So we managed to increase the porosity up to 75%, which allow us to reduce the refractive index down to 1.12. And to keep the optical quality and the clarity, what we need to do there is not to control the crystal size like we did for TiO2, is now to control the size of the pores. So we have very small pores below 10 nanometer, and this is why we have no scattering or absorption, because the pores are very small. Is a key. And so now, so far, what we've shown is that kind of standard approaches to make the metasurfaces. So basically, you start with a thick layer of the high refractiveness material, you etch it, and then you do the encapsulation. One of the challenges that a lot of customers today have with etching TiO2 is that it's kind of difficult material to etch. So they have to come up with very slow etching processes. Sometimes they use atomic layer etching, which is quite slow. So we have been working on another approach at Solnil, is that we went the other way around. So what we did first is, can we just, instead, because our materials are liquid, just make holes in silica, because silica is very easy to etch, especially porous silica. So you can very easily etch very deep grooves into silica. And then you keep using our material, which is liquid, we can fill the gaps. So this is what we have been working for the past year. And it's a process that now is working well and running for small aspect ratio, with an aspect ratio of 1, and regular patterns. So now it's something that is scalable to large area. So basically, we just start with nano imprinting a low refractive index material, and by using specific deposition parameters and specific chemistry, we managed to have only a kind of selective deposition in the holes. So today it's very efficient and it works quite well for standard patterns, uniform. And now we're in the process of developing this further for metasurfaces and more complex designs. And so, as conclusion, so what we have been working at Solnil is really to extend the range of refractive index, to really simplify the fabrication process of optical metasurfaces. You can find more details on our website for each material. And today we will start maybe to provide, we're interested in partnering with end users or design companies who have some ideas about metasurfaces, who would like to work with us to show how our materials could enable the designs. And thank you.